So here we have our power supply and management system, which is basically what we have in a cell phone. And here over in the highlighted region is our focus today. And you can see we have amplifiers, mixers, bandpass filters, diplexers, and an antenna going from right to left. And we will go through this from right to left. Here in purple you can see that system in the baseband input signal. So let's get started. Here is a breakdown of the beginning of that system, beginning of that path of the amplifier here on the right, going to the mixer. And we have a signal x1 of t, which represents our voice signal in a cell phone. And x2 of t is a cosine of omega naught t, which will be our carrier for the signal. And you can see our y of t is x1 of t times x2 of t. And when you take the continuous time Fourier transform, our spectrum of the signal is going to be the original x1 shifted to the right and to the left. And you can see visually here how that will look. And this only works because our x of j omega is a bounded signal. And our y of j omega here has been sampled correctly and doesn't have any aliasing. And you can see that the middle of each signal is at omega naught and negative omega naught. And then it's going to pass through another amplifier. This amplifier is going to multiply the signal here, and we want to change the frequency. And that is because most environments are frequency selective and will only transmit well within a specific frequency range. I will go into this a little more throughout the presentation, but different mediums such as air, water, even solid material, and the vacuum of space all have very different properties for transmitting signals and may have an optimal range. And since voice signal is around 3 kilohertz, we, using calculations from EMAG, see that the signal, or our receiving antenna would have to be huge unless we increase this frequency. So I'm going to demonstrate here how most environments are frequency selective. So say we have salt water and we want to transmit a signal down to a submarine. So to transmit through seawater, we need to increase the skin depth, or the penetration of our signal, by increasing the frequency. Otherwise, our signal will not go down deep enough into the surface, and our submarine will never hear our signal. And make note of the yellow submarine. And since our voice signal is around 3 kilohertz, we would need a huge antenna in order to receive the signal, unless we increase the frequency. So you can see here that lambda equals c over the frequency, which is the speed of light over the frequency. And when we calculate that out, we get 10 to the 5 meters, which is 100 kilometers. Now imagine trying to have an antenna that huge on your cell phone. I don't think you'd get very much done, and it wouldn't be very useful. So we're going to increase our voice signal, and the standard for cell phones is around 2.4 gigahertz. And when we calculate that out using C over F, we get approximately 0.1 meters, which is a lot more reasonable for our antennas on cell phones. The next thing that our signal is going to move through is the bandpass filter. So with bandpass filters, or any filters, we have a high-pass filter and a low-pass filter here. There is a trade-off between the transition rate and the cutoff of our filter. And in order to get a nice clean filter, we're going to optimize both of those in our high-pass filter and our low-pass filter, and we're going to multiply those together by putting them in series. And when we put those in series, we end up adding the spectrums of our high-pass filter and low-pass filter, and the common frequencies that they both allow through them will become the frequency range of our bandpass filter. And we want to use a bandpass filter because we don't want that replicated range, or that replicated signal to be our output in the very end. We just want to take one of those. We just want to clean up our signal by using the bandpass here. And then finally, we're going to get to our antenna, and our cell phones have lots of antennas. And that is because, as we saw in the equation where we're calculating the wavelength of our antenna, we know that every antenna must be specialized for different signals coming in with different frequencies. So because of this, and because of the need of specialization of antennas, we have lots of them in our cell phones. So we have around 10 to 11 in our current smartphones today, and they have different functions such as receiving calls, GPS, knowing the temperature, lots of different things. And so we talked about having a dipole antenna, which is a very basic antenna, and that's the picture up here on the left of the donut shape. And the actual antenna is just a straight up and down dipole, but our E fields coming off of this antenna come out the top and loop back around and look like this donut shape. And this is just one type of antenna, but there are lots of antennas out there, and they can be very customized for different functions, and you can even add them in different configurations to create different E field patterns. And it's very useful and very interesting. And our antenna size used to be in the order of the signal or smaller. And here are some properties here. You can see demodulation, which is transferring a signal back into the correct audible range after transmission. We talked about signal carriers, so as long as the signal is periodic for your carrier, it's good because it'll hide the cosines inside the carrier signal, and you can take those out again later. And always remember your Shannon-Nyquist sampling rate to avoid aliasing. And we have different types of signal. We have AM, which doesn't work very well in stormy weather because the signal of lightning will superimpose with the radio signals and cause problems. And then FM radio is fine in bad weather because it has a constant amplitude and it's only frequency shifted to separate out the different frequencies. And then PM is used for radar, and the signal determines the phase of the carrier here. So thank you very much, and I hope you found this informative.